So what I've just spelled out to you is the requirement for inflation. And if you're thinking critically about it, you might say, well, hang on, you had these fine-tuning problems. You didn't know why the universe was flat, you didn't know why it had the same temperature everywhere. But haven't I just replaced this with another fine-tuning problem? Because what causes inflation? Right, I've hypothesized something as a solution to a problem and I haven't explained at all why it has to exist in the first place. And so it's worth thinking about what the cause of inflation may actually be. And I will notice, at the moment at least, this is still speculation, it's theory. We don't have clear observations that tell us what ideas of inflations are right. And so you've got to have some sort of energy, right? A bit like dark energy now, the cosmological constant is potentially powering a universal expansion. You need some sort of energy. And where are you going to get it from? And so the idea is that it comes from a scalar field associated with spontaneous symmetry breaking. And you may or you may not have heard those two words before. They're both kind of fashionable words in physics. They're quite popular. But you may not know what either of them are. And so I should probably spell out what they are before I go any further. So the idea of a scalar field is it's just something which has a value at every point in space. And so a really easy example of that is I can take the temperature in many different places across the world or anywhere in the universe, right? There is a temperature of every point in space. The temperature is therefore a scalar field. And that's different from a vector field, which might be a gravitational field, for example, which has a magnitude and a direction at any point in space. A scalar field does not. In particle physics parlance, scalar fields describe spin-zero particles. Spin-zero particles aren't so easy to come up with because the photon has a spin of 1, quarks have spins of 0.5, they're all fermions and so on. So it's a boson, but it's a boson with no spin. Not so easy to do, so one that does have that is the Higgs boson. And so that's what a scalar field is. And in a homogeneous isotropic universe, of course, a scalar field is the same everywhere. But it can be time variable. So it can decay, but it is a scalar field. And it's the same value at all points. So basically you create some field, you tap the energy from that field, you remove the energy from it, and that powers your expansion. So essentially, you take the heat energy in the room, you suck it all out till you get absolute zero, and you use that energy to power expansion. So you use your power in your scalar field to power the expansion of the universe. And then we come to the idea of spontaneous symmetry breaking. And to actually explain what this is, I need to back up a little bit and talk about the fundamental forces. And this came up a bit last week, and I realised it wasn't something you were familiar with, so I will sort of back up and talk in a little bit more detail about what that is. And so, if I look today at the forces, I can basically think about several different forces. So I can think about gravity, I can think about electromagnetism, right? They're forces which are familiar to you. I can think about the weak nuclear force, and the weak nuclear force is the force which is responsible for radioactive decays and neutrino production and so forth. I talked about weak forces because weak forces are dominating the neutron-proton interactions in the early universe. So they dominate radioactive decays, and we have the strong force, which mediates interactions between quarks and so forth and holds atomic nuclei together. It's genuinely very strong. And they're my four forces. Now, if I think about my x-axis here being energy, and to put it another way, I could also think about my x-axis in the other direction in the universe being time. So the universe is higher energy at early times, lower energy at later times. And so we know that as you get to higher and higher energy, the weak and the electromagnetic force combine to make something called the electroweak force. And we expect that at some point later on, that will merge with the strong force and make something called the grand unified force, or the grand unified theory. So grand unified force of the electromagnetic force, the strong force and the weak force. And we even think that at some point eventually, I draw this very badly, we might put in gravity and get to the very modestly named theory of everything. So these are the concepts that essentially you can have the forces combining, becoming explained by one model. So electromagnetism plus the weak at high enough energy becomes the electroweak force. That won the Nobel Prize in 1979. Eventually at higher energies you get a grand unified force, and eventually you get a theory of everything. Can't actually write down either of those at the moment, but people of course are working very actively at it. So things like string theory are attempts to write theories of everything. And part of the problem comes from gravity, as we'll see shortly. But of course, if I run the other way with time, then these forces are uncoupling. And it turns out that about 10 to the minus 36 seconds, and of course we don't know exactly, you have the GUT phase transition. You separate into electroweak and strong. And at that point, you can have the production of a scalar field through the breaking of symmetries. And the breaking of symmetries means that the two forces don't act the same, because there was a symmetry that made them the same thing. That symmetry breaks and they're no longer. You also, and again I'm not going to go into this because going into this gets messy and difficult very quickly, you also get so-called topological defects. And those topological defects include, surprise, surprise, magnetic monopoles and cosmic strings, both of which you may or may not have heard of, and if you haven't, doesn't matter, but there are other things that happen. And so the idea is that the scalar field is produced by this transition, and often you'll see it called the inflaton field. And that is not a typo or me writing badly, though doubtless I do. Inflaton field is the field which powers inflation. So we can't write down exactly the details of inflation. We can come up with different ideas about how it happens, but perhaps the more important point is that there are at least physical arguments for why there was some source of energy which existed at those early cosmic epochs that could have powered inflation. So it's not just a wild idea. There are some physical arguments for why it should have happened.